As the title of this section suggests, we're going to take derivatives and learn how to reverse the process. Just like addition has its subtraction and multiplication has its division, and even trig functions have arc trig functions. Derivatives have antiderivatives. So I'm going to show you how that process works. Now, it's popular in calculus courses to use a capital F to be an antiderivative of a lowercase f. So I'll do the same kind of stuff. So we say that capital F of x is an antiderivative of little f of x if capital F prime of x equals little f of x. As an example, suppose I choose a little f of x equal to x. Find an antiderivative of that. So we have to think of what we would use for capital f of x in this case. So capital F of x, what can you think of things whose derivative is x? Well, you might try to do x squared, but when you take its derivative, you get 2x. So that's not quite the same as x. That 2 is in the way. But now if I divide, if I could instead have divided by 2, and that would have canceled out the 2 that I had there. So as a capital F of x, I can try x squared divided by 2. That way, f prime of x will be 2x over 2, and then the 2's will cancel. So there you go. So x squared over 2 is an antiderivative. I'm using, now, the word "an" is important because there's multiple antiderivatives. Another example. This time find an antiderivative of little f of x equal to 0. Then, easy enough, capital F of x could be 1. Derivative of 1 is 0. However, it's not so simple as that. If capital F of x equaled 10, then its derivative would also be 0. If capital F of x equals negative 3, its derivative is 0. If capital F of x equals 0, its derivative is 0. In fact, if capital F of x equals any real number, its derivative is 0. So many times we will simply write capital F of x equals c, where c is a constant. And we'll leave it at that. That'll take care of any possible number that f of x could be in this case. If I just say c, I'm allowing for literally any real number to be a possible answer. So basically, if I write capital F of x equals c, I'm writing a range of possibilities, a whole collection of answers as being possible antiderivatives. That's why I said find an antiderivative. If I ask you to find all the antiderivatives, you might write f of x equals c, where c is just a constant. Now, one of the coolest symbols in all of math is the one I just wrote there. What I have there is called an indefinite integral. And you've got an f of x followed by a d of x. And that equals all the possible antiderivatives of f of x. This time I'm using little f of x. As I mentioned, the integral symbol, that long S, is just the integral symbol. So when I write that, I'll typically say the integral of f of x, or the long S symbol f of x dx. The whole thing is usually just called the indefinite integral of f of x. We'll have a definite integral later on, but for right now, we're working with just the indefinite one. As an example, what is the indefinite integral of x followed by dx? So I'll typically just say the integral of x. The dx will be assumed automatically. And we saw, when you looked at the antiderivatives that we had before, x squared over 2 was one that worked. And just so we indicate all the possible answers, I'll put plus c at the end of the answer so that it represents all possible antiderivatives of the function. How about the integral of 1? Well, what kind of functions have a derivative equal to 1? Well, x is one of them. And so that you have one, that means all the rest of them can be gotten by adding a c. So all of the functions whose derivative is 1 look like x plus c. How about the integral of cosine of x? Well, the derivative of sine of x equals cosine of x. So the integral of cosine of x equals sine of x plus c. The integral of e to the x, that equals, well, the derivative of e to the x is e to the x, so the integral of e to the x is e to the x plus c. The integral of 1 over x dx, that equals the natural log of x plus c. However, that is not all solutions. That's not all antiderivatives. If you'll remember, sometime a while back ago, we showed that the derivative of the natural log of the absolute value of x was 1 over x. So I should include the absolute value, because the absolute value being around there says that x will be good for anything except 0, and 1 over x is saying the same thing. So it makes sense to put those absolute values around there. Now the power rule, we know the derivative of x to the n is nx to the n minus 1. Let's look at that in detail. We bring the power down front. That's the first step in the process. So we bring the power down front, and then, that means this step happens after that, and then subtract 1 from the exponent. Now I have to rephrase this so that I can do a reversible operation. Bring the power down front is not as reversible as you think it is. So let me get rid of that statement and make it more mathematical. What we really did is we're multiplying by n. So the very first thing we do is multiply by the exponent. And then subtract 1 from the exponent. So how would that look if we reversed the process? So instead, what is the integral of x to the n going to look like? So I need to reverse the process by taking what I did last time and reversing the order that I did it. So if I multiplied first and then subtracted 1 second, I will reverse it and say add 1 to the exponent and then divide by the exponent. That's exactly reversing what we did in the first part. So, the integral of x to the n, if I add 1 to the exponent, I'm going to get x to the n plus 1. And then if I divide by that exponent, I'm going to divide by n plus 1. And then, of course, you add plus c, because that's what we do for all of these. So you could think of this as the power rule for integrals. The integral of x to the n is x to the n plus 1 over n plus 1 plus c. And I guess I should mention the only n that doesn't work for is -1. It works for all real numbers otherwise. Now, if I have the derivative of capital F of x equals little f of x, give me a moment to correct my mistakes. Then the integral of little f of x equals capital F of x. That's what we have been talking about this whole time. It's a inverse relationship. Similarly, if d over d of x of capital F of x plus capital G of x, well, that equals capital F prime of x plus capital G prime of x. What it means is I applied the derivative to each of the f and the g separately, and I could then add them to after taking the derivatives. Well, the same kind of a thing is going to work with the integrals. Just as the derivatives, you were able to break up sums and differences and things like that, you'll be able to do the same thing here. So if I have the integral of f prime plus g prime, I can consider it like f of x plus g of x, that quantity prime, because f of x plus g of x, the derivative of that quantity is f prime of x plus g prime of x. So I can get f of x plus g of x plus c as if I had integrated them separately. Now, let me just show you what I'm talking about. If I integrate separately, f prime of x, the integral of f prime plus the integral of g prime, when you do the integral of f prime, you might want to say it's f of x plus a c, like c1. And then when you do g of x, g prime, you might want to say, well, that's g of x plus, say, another constant. And then you might think that there's two constants hanging around, but that's not the way we have to work at all. It's okay if we take the c1 and the c2 and just combine it into one solid constant. After all, the sum of two numbers is still a number, so that's not a big deal. So you'll find it easier just to integrate piece by piece without actually breaking the integral up into individual pieces. You'll find it just quicker to do. So anyways, so that you don't have to go through that process every time, the integral of f plus g is the same as the integral of f plus the integral of g. That's all I've been trying to say. All right, let's try the integral of the square root of x minus 1 over the square root of x. And I will tacitly use the stuff I just talked about. I advise you to change these to exponential form. So square root of x I'm going to write as x to the 1/2, and 1 over the square root of x I'm going to write as x to the negative 1/2. Now apply the rules of integration. X to the 1/2, if you add 1 to 1/2, you get 3/2. Then you divide by that 3/2. Minus, now x to the negative 1/2, you add 1 to get x to the 1/2, and then you divide by that 1/2, and then add c. Now you can simplify, because you can take, when you're dividing by the 3/2, you can turn it upside down and make it a 2/3. So you have 2/3 x to the 3/2 minus 2x to the 1/2 plus c. All right, another example. The integral of sine of x. Well, whose derivative is sine of x? Well, you don't have anything directly, like the derivative of cosine of x is negative sine of x. So it's not quite directly equal to sine of x. However, if I were to take the negative cosine of x, if I took the derivative of negative cosine of x, then the negative there with the negative that you take when you take the derivative, they would cancel each other out. So the integral of sine of x is negative cosine of x plus c. Let's try the integral of t to the 5th minus 3t squared plus 1, all of that over t dt. Now, it doesn't care what the variable of integration is, so long as the dt, the variable there, matches the variable that we're working with. So in this case, the dt indicates that I'm carrying out all my work with regards to the variable t. Now, what I want to do is break this up into 3 fractions. So I'll have t to the 5th over t minus 3t squared over t plus 1 over t dt. Now, when I have a big expression inside of the integral, I like to put parentheses around it. The t to the 5th over t is t to the 4th. 3t squared over t is 3t. So I have minus 3t plus 1 over t dt. So the t to the 4th becomes t to the 5th over 5. The t becomes t squared over 2, and the 1 over t becomes the natural log of the absolute value of t. Now, what I'm doing here is I broke it up into 3 integrals because you can, but I don't advise doing it this way. But if you want to apply each of the rules individually, maybe this isn't something that you need to do. Anyways, the t to the 4th integral, you could think of that as being t to the 5th over 5. You add 1 to the exponent and divide by that exponent. You get t to the 5, and you might think that you want to put a plus c1 because that's one integration. Then the next one, you have negative 3 times the integral of t, and so you'll have t squared over 2 for that particular integral, and then you might have a second constant because of that one. And the last one, you'll have the natural log of the absolute value of t, and then you might have a c3. What I'm advising is you can do it all at once, because you can just take all that c1, that c2, and that c3, combine them all together into one big C, and that's fine. So you don't have to break it up. You just know that that is something we already do and it works. So I would simply go directly to my answer and go to t to the 5th over 5 minus 3, and I'll even go 3 halves t squared. In a minute you'll see why I do that, and then plus the natural log of the absolute value of t plus 1c, and that will do the work of all the other c's. So I mentioned why we put the plus c. Well, because its derivative is 0. That's why. So you'll get f prime whether there's a c there or not. So by putting a plus c, you're simply writing all the possible answers that you can have. In fact, we had a theorem back when we did the mean value theorem that said if f prime of x equals g prime of x on an interval I, then f of x minus g of x was equal to a constant on that interval. But that's the same as f of x equals g of x plus c on that same interval. So that's why we write the f of x plus c for our final answers. Well, let's develop some integration formulas. And anytime you've got a derivative, you've got an integration. Let's take a look at an example. Let a be a non-zero number. The derivative with respect to x of arctangent of x over a equals, now remember the derivative of arctan is 1 over 1 plus something squared. Well, in this case the something is x over a, so we'll have x over a squared. But don't forget, you still have to take the derivative of the x over a according to the chain rule, and that'll give you a 1 over a. Now I'm going to do a little work simplifying this so that I can come up with a good looking formula. We'll have 1 over 1 plus, what I'm going to try to do, let me multiply that bottom out. So I got x squared over a squared times 1 over a. Let me get in the denominator a common denominator down there. So I'll rewrite the 1 as a squared over a squared. Now I can combine the fractions in the denominator, and I'll get 1 over a plus x squared. That part is over a squared, and don't forget times 1 over a. Next, I will be able to flip the fraction in the denominator, so I'll get a squared over a squared plus x squared times 1 over a. And then I'll be able to cancel out an a. So I have a formula for this derivative. The derivative of tan inverse of x over a equals a over a squared plus x squared. So, since I have that formula, I immediately get an integral formula. The integral of a over a squared plus x squared dx equals arctangent of x over a plus c. Now, it's unusual for problems to come exactly in that form, as you'll see from the example that I want to do that illustrates how you use formulas like this. Sometimes you have to be a little inventive. Suppose I have the integral of 5 over 7 plus x squared dx. Now if you look, I don't, if my a is 5, well my a squared is wrong, so I somehow got to fix this stuff. The 7 is, okay, now what I can do is rewrite the 7 as radical 7 squared. But that means then my a is radical 7. And I've got a 5 where the a is supposed to be. So how do I fix that? So the radical 7 was easy enough to get down there. I have a feeling it's easier to fix that than it is the 5. Now, I can pull the 5 out front because it's just a multiple. Okay, now I got 1 over the square root of 7 squared plus x squared dx. Now it's still not quite, because I have an a squared, but the a is not 1. The a is supposed to be radical 7, so that 1 needs to be a radical 7. So what do I do to make that happen? Well, put radical 7 there. And then I've got radical 7 squared plus x squared. So I put basically radical 7 where I wanted it to be. How do you do that and get away with it? Well, you simply divide by radical 7 out front, because you can pull in or out these multiples. So that part, the part in front of the integral, is not part of the formula. Only the integral is part of the formula. So you can see that I now have an a squared and an a in the right spots, with the a being radical 7, so I can write my answer now. This is 5 over radical 7 times arctangent of x over radical 7 plus c. Another derivative we can do to develop a formula. The derivative of tangent of ax is secant squared of ax, but then don't forget to take the derivative of ax and you'll get an a. However, most people prefer to write it as put the a in front of the secant squared, so the derivative of tangent of ax is instead a secant squared ax. It just seems to be more comfortable for us to have the a in front, like a coefficient. Coefficients seem to be in the front more often than not. Let's try another example. 10 secant squared of 3x dx. And if I'm trying to do this, I'm trying to match it up with the tangent of ax. So I need an a in front, and I need an a before the x inside of the parentheses. Well, there's nothing you can really do inside the parentheses, so I'm pretty much stuck with a being equal to 3. So I'll have my secant squared 3x dx. So the 10 I pulled out front, no big deal. I can simply put a 3, that's the a that I want, in front of the secant squared inside the integral, so long as I divide by it also. Now the 10/3 simply becomes a coefficient. And so I can apply the exact formula now. 10/3 times tangent of 3x plus c. All right, let's try the integral of 2w minus 3 times 3w plus 2. And right now, we don't have any formulas for a product or anything like that. We're going to approach things in the most straightforward possible vein you can imagine. So I'm simply going to do what you would do had you never seen this before, and that would be to FOIL the whole thing out. So I'm going to do just that. I'll get 6w squared plus 4w minus 9w is minus 5w minus 6 dw. And the only reason I picked w was to indicate that the variable is unimportant in this process. Let's see, anyways, w squared is w cubed over 3. W is w squared over 2. and the minus 6 part becomes minus 6w. So that, think of there as being a 1 attached to the 6, I guess. Whatever you got to do. And then, of course, plus c. I'm going to simplify and also show you what I do when I write fractions, like the minus 5 halves. I prefer to write minus 5 halves w squared versus 5 times w squared over 2. I like the idea of it serving as something like a coefficient, I suppose. So 2w cubed minus 5 halves w squared minus 6w plus c is our final answer. All right, now we switch a little bit to physics, which is Newton's applications. He was the physicist who invented calculus to actually do the science he was working on. You might remember the apple falling from the tree, I suppose. It's supposed to have been a Newton thing. Well, anyways, we're going to look at something like that. If s of t is the position of a moving object, then s prime of t is the velocity. So we usually s prime of t equals v of t. Similarly, v prime of t equals a of t, and a is the acceleration of the object. Now, Newton was concerned with free-falling objects, although there's been complications to it introduced since then, but you might consider ours to be the Newton experiments where there's just gravity and no wind or anything like that. It's like falling in a vacuum. So, with all of those stipulations in mind, here's an example. So suppose we throw an object straight downward. At 2 meters per second. So this is straight up and down motion. It's going straight down. Additionally, suppose the height that it was thrown from was 200 meters. I want you to determine formulas for the position, s of t, and the velocity, v of t. Well, before we can do any of that, I probably should remind you a little bit about the physics of free-falling objects. There's not much to remind you, just a very, very little. When an object is dropped, in our scenario, the only force acting on it is gravity, and gravity is pulling it downwards toward the Earth. Now, we call that object being in free fall. Even though you took the object and threw it downward, in this case, it's still considered free fall because the moment you let go of the object, there is no force acting on the object except gravity. Now the acceleration due to gravity is negative 9.8 meters per second squared. So that's what we'll use for our acceleration, negative 9.8 meters per second squared. The reason why it's negative is because the gravity is pulling it downward. If it were positive, it would be being forced upward. So that's why the negative is there. Now first, we make note that v prime equals a of t, so I can immediately reverse this to an integral where v of t equals the integral of a of t dt. And now I'll go ahead and plug in the acceleration of negative 9.8 dt. Now that negative 9.8 can be pulled into the front of the integral, can be factored out, and what would be left inside is a 1 dt. Now a lot of authors will just simply write dt, which is fine. It's just I'm not doing it right now until I feel like you're more comfortable with these integrals. Anyways, the integral of 1 dt is equal to t. So our velocity then is given by negative 9.8 t, and then don't forget there's a constant attached anytime you do an indefinite integral. Now in this particular example, we could calculate the constant in this problem because we're given extra information. We're told, for example, the initial velocity. That was how fast the velocity was when the ball was initially, the object was initially thrown. That would be v of 0, or velocity evaluated at 0 seconds, is -2. Negative because it was thrown downward. So anyways, anytime I give you something like this, a number at the beginning of the experiment or whatever, it's called the initial quantity. So anyways, let me plug it into the formula I have for v of t. I have v of 0 will equal negative 9.8 times 0 plus c. v of 0 is -2, so when the negative 9.8 times 0 disappears, I have -2 equals c. Therefore, my formula for velocity is negative 9.8 t minus 2. Next, we make note that s prime of t equals v of t. To create an integral, s of t equals the integral v of t dt. And now in place of vt, I will put negative 9.8 t minus 2. And then don't forget the dt. Now we're ready to do the antiderivative. The t, the negative 9.8 is no big deal. That's just a coefficient. I explained it before. You can just focus on the t. The integral of t is t, well, it's t to the 1 right now. So if you increase the exponent, you get t squared and then divide by 2. So I have negative 9.8 times t squared over 2 minus 2. Now think of that 2 as being 2 times 1. That way its antiderivative is t. And then don't forget to add c at the end. So my formula for s of t is negative 9.8 times t squared over 2 minus 2t plus c. Now the initial position is 200. That is, s of 0 equals 200. So I can put t equal to 0 into this last equation to uncover the value of c. So let's see, s of 0 equals 200. That's what we're given. S of 0, according to this formula, is negative 9.8. Now I think about it, I'm going to simplify that negative 9.8 and 2 and make it negative 4.9 t squared. So this way, when I do this, I'll have negative 4.9 0 squared minus 2 times 0 plus c. So all those things zero out, and I end up with c equals 200. So my formula for position is negative 4.9 t squared minus 2t plus 200.